Good afternoon, Daniel, my brother. You are older than me. Do you still feel the pain? Daniel, has been here since, I don't even want to tell you people. This man, I think he took Physics 204 and 205 while he was waiting for this class to start. He's the man. Okay, no, you're all the women. Okay, good afternoon. I'm just being silly. I'm sorry. I'm in a good mood because I get to teach physics for a living. Good afternoon, Daniel. Good afternoon, Nikaya. Who's also been here since 1977. Believe me. I mean, Woodstock happened, then whatever. But that happened in 69. Good afternoon, Nikaya. Good afternoon, Jerry. Good afternoon, Ashley. Good afternoon, Jenna. Hi, Sam. Good afternoon, Alyssa. Also, good afternoon, Camilla, who's totally showing a picture. Good afternoon, Sam, who's totally showing a picture. Good afternoon, Nikaya, who's totally showing a letter of the alphabet with a color purple, which totally counts for everything in the world. Did I say good afternoon, Alyssa? I think I did. I'm sorry if I did. Good afternoon, Ashley. Oh, I said that. Sorry. Okay. I don't know. I'm being silly. You know why I'm being silly? Because I'm not on a street corner. It's like you could almost tell, can't you? It's okay. Okay. No, I'm also being silly. Okay, so we're just gonna do some physics. I hope you can hear me right, I think. Yeah. Yes, no, yeah, exactly. Okay, I think that means you can hear me. I'll have to see that. Wait. Yeah. Oh. Okay. So what Sam said in the chat is funny, and yes. Oh, pardon me for a second. Bye. Have a good thing. Right. So instead of being harassed, I'm harassing people with my right brain. I'm sorry. Yes. I to this day, honestly, I don't know if it's a left brain, right thing. But I still don't know which brain is supposed to be which. I know I'm missing at least a third of each hemisphere. But okay, wait, real quick. But hello, and that is funny, and it's funny now. It wasn't funny then. But yes, no, sorry. A real question in the direct chat that I do want to answer, although I almost feel, well, okay, this is I almost feel uncomfortable answering this like in public, but so someone in direct chat is asking legitimately, like, if and when anybody subscribes to the YouTube channel, which of course I totally appreciate, which is not required and which is not the only way to get points. I hasten to, but how do we upload that to the portal on Google Classroom? Really good question. And the answer is, if you first of all, I really honestly, I would believe you even if, no problem. Sorry, different thing in the direct chat. Okay, I'm gonna try. Direct chat is such a, who says remote teaching doesn't work? Well, it just doesn't work if it's me. Okay, yeah. So no, if you do anything, it is true that if you do anything with YouTube at all, which doesn't mean you have to subscribe, if you even like use one video to help you at all, or like, because you missed a class, or you need some material like reinforced, and you like even play, I think, 3 minutes of one video, just if you use it as a resource in any way, it's totally true that you do get game points, participation points for that. It doesn't have to be subscribing, although obviously I love that. And if you do, right, say you do subscribe, or you just do anything with any YouTube video, just screenshot it, like the fact that you did that, and just put that into the Google Classroom portal. Truth told, and with all Google Classroom portals for all so legit question, just screenshot it if you can, and then and submit that into the portal, and you don't really have to explain or anything like that. But truth is, to all of you, with all of the game participation points assignment stuff, which I really do love, and a new one of which was recently uploaded and maybe requires some explanation. But with all of them, it's really not about proving anything to me. The honest truth of the matter is, I mean, especially when it comes to YouTube, which is sort of a funny thing anyway, like, you don't have to prove anything. It's more just about the moment of self-reflection and self-reminder to yourself that is entailed by filling out a game points portal. And it's about like reminding or alerting me and like requesting for me that you get the points. So if something went wrong, if you did subscribe to the channel, or you used a video, even if you write a sentence that says like, I used this video to better understand the wave equation because it went too fast for me in class or something. That is sufficient. Like, you don't, this is not about you proving something. Your word is good with me. I mean, until it's like abused. So honestly, for the person who's asking in direct chat, like, how do you prove, or, you know, how do you upload that you subscribed? Even if you have a problem screenshotting or something, I will believe you if you just write a sentence that says, I subscribed, or, you know, or I used a video for this. Okay. It's just partly just because it's a resource that I, you know, hope that you guys can take advantage of, but it is not. Okay. So that's that. Hold on, other people coming. Oh, thank you. Oh, and so, for example, the person that just asked that in the direct chat, who asked like, and yeah, the person who just asked that, then I answered, and then they said, thank you very much in the direct chat. That I want to remind everybody, she or he now can also submit. I know I say this every time, but I mean, the more it actually happens, it makes me so happy. I just want to reinforce that the person who was in direct chat who just asked me about, like, how do you, you know, upload evidence that you used a YouTube thing? Then I gave this long explanation, and then she or he said, thank you very much. She or he can should totally now submit that thank you very much thing into the closing a conversational path portal. Ideally, just a quick screenshot, but even if not, just writing out, like, remember, I'm the one that asked you about the YouTube, blah, blah, blah. I asked you in direct chat, then you answered, and then I wrote, thank you very much in the chat. It's not, and that is totally points. Like, and believe me, I know it just happened. I just spoke about it. And if I really wanted to, I could replay this YouTube video and prove to myself that it just happened, right? Like, so you guys don't have to prove anything to me. It's more like reminding me and reminding yourself and just like flagging that moment in time when we were good human beings to one another, which really, closing a conversational path so is being a good human being, especially when you have a blabbermouth like me who is behind the wheel. Okay. So that was that question. Also, no problem about the lateness. Thank you, direct chat people who are saying thank you. I mean, sorry about the snip tool. Oh, is my best friend for all the game terms. That's hilarious. I think I know the snip tool. I'm not even sure. All right. Okay. Or, oh, now funny. Okay. I want to say to all of you and to 11,000 of your best friends who are perhaps watching also, like, really cool and I know that one thing that does not show up in the video, I do understand that you guys can't see the chat like not on a YouTube video anyway. I do get that, and maybe someday, maybe that's why we should be doing Discord. I don't know, but something interesting is happening in the chat now that I want to mark. Like, the person in the direct chat asked me this about how do you submit evidence to, you know, to a game portal thing. And then I babbled about it, and then they thanked me. So that was nice. But meanwhile, in the chat, some people are helping out in the public chat. Like Ashley just wrote, like, just take a screenshot of a picture. I think that works. And Sam wrote, like, the snip tool is my best friend for all the game turns. What I want to make clear is, so that means two people just like acknowledge the existence of another person in there. And I mean this, two people in the Zoom room took a moment to try to help out a colleague that they don't even know who it is, right? We don't, I mean, maybe they do, but like, they don't necessarily know that it's their friend or something. I mean, it's someone in direct chat that I'm talking about, but they just took a moment to acknowledge that question in direct chat and give like some helpful feedback answers to that person. And I'm taking those as helpful. I mean, they were funny, or one of them was funny, but like, they are helpful feedback. They're certainly not disrespectful I hope, in my judgment, like, both of them are just helpful answers to the other person. And here's what I want to say, and I hope the person in direct chat took them that way. And like, of course, the person in direct chat doesn't have to take their advice. Like, no one's saying that. They could just ignore it. But the fact that two people in the room are like acknowledging the legitimacy of a question raised by another person in the room, and even just like trying to do anything with it at all, even just acknowledge it, let alone actually give a constructive answer, again, I think is a really important. I mean, call me a cheesy, call me like left brainy or whatever, but I think that like being heard as a person, especially in a remote learning environment and all that, like actually knowing that someone else is paying attention to the fact that you're saying anything, let alone that the professor is like taking time to blah, 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 blah. Like, I don't know. I need this in my life. I need people cross-pollinating and cross-communicating and showing that if nothing else, I'm not the only one in the room, right? Therefore, so what's my point? If I had one, would I be doing this for a living? No, what's my point? Wait, so why you say ugh? So thank you, Ashley. I think so. She writes ugh. I literally love this. Okay, well, thank you. No, me too. I love the love. And as was it Michelangelo who said, I want to want what I do not want, or something like that. Maybe I do not want what. Anyway, I want to be Michelangelo. It's like that simple. But well, I guess I got to start here, don't I? No. What I'm trying to say desperately is that I opened up a new game portal recently. I think you saw it in your Google Classroom maybe like a week ago, but I don't think I've explicitly explained it or addressed it. But the new game portal is called Multiplayer Co-op. Okay, and it's meant to be that. And the basic point of the portal is anytime any one of you actually does anything in the chat or in voice to somehow constructively acknowledge the contribution of somebody else, like which just happened, right? Like any one of you either provides an answer to, or a suggestion to someone, or even just like Sam got 3, and then Ashley says, yeah, I got 3 also, like as an answer to a question in physics. Like God forbid we should talk about that, right? If even like one person says, I got the answer 3, and even if another person just says like, instead of just saying 3, they say like, yes, I also got 3, or like Sam, I got 3, or I agree with Sam, or even I respectfully disagree with Sam and I actually got 3.14, you know, which you might remember from some films as pi. Like if that happens, whoever acknowledges the other person should submit that for points to the multiplayer co-op. Like if you somehow pivot off another person in a respectful way, which could even mean disagreeing as long as it's respectful, right? If somehow you're showing that their contribution like meant something, even if it's just repeating their contribution, then you submit that for points, submit both of your names. Like make there, you have to, I don't care about proof, but you have to be specific. Like they said this thing, then I said that thing, submit that, you will get points. And here, guess what? So will the other person. Well, I think they have to submit also, but they will too. If you're on the receiving end or the non-receiving end, you'll both get points. Okay, it's multiplayer co-op. We're trying to come together as a people here. Okay, so and examples just happened. Like I think it was, I'm not going to scroll back, but like and by the way, I know that the people just did it, like Ashley and Sam just acknowledged someone. They don't even know who it was, so they'll have to write like it was in direct chat. We don't know, but I'll, you know, as long as you write that, I'll remember. So, and the direct chat person knows who she or he is. She or he can also submit, like when I was in direct chat that one time, like then these people came to my, and they rallied around and they mentioned like apps that I totally don't ever want to use, but thank you anyway. Okay, so you get points for actually like being collegial, and so does your colleague. So yay, that's what I'm trying to say. All right, okay. So, okay, that was all. Another word from our spiritual sponsor. Okay, we have to do some physics, right? Right. Oh, and I think I'm behind. I think I owe you some game turns. I apologize. Okay, where are we? We're up to this. Yes, and I may, hold on, just adjust the light. I'm sorry, but we, well, as usual. So like the equation that's in the middle of the board right now is where I believe we had just gotten to in class last Thursday. I think we just gotten to it. It's a big deal, but I think we landed on that punchline right at the end. So I'm going to back up a little bit, try to say what it was, but then we're going to spend a while unpacking it. Like that's a big equation. I mean, it's one of my favorite equations. Some of my best friends are that equation. Then the thing underneath it, just to be clear, like I think this is sometimes how I like to, the equation underneath it is where I want to get to today. Like that's not meant to be old news. That's meant to be like the next goal. So I'm not expecting that you recognize it necessarily. You might from lab, but I'm not sure. But so just to be clear, the thing in the middle, you should be thinking, yeah, like I've seen that, but I still don't get it. I hope he explains it more or something. And I think you've seen it in the lab, but the thing underneath is where I'm going to try to go with that today in the next hour or whatever. I just want to adjust the lighting if I can. Pardon me for a second. I don't know if I did anything. I'm not sure if I did anything. maybe not. Okay. 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 So the equation that just flipped around for no reason, the equation in the middle, the thing in the middle of the page is called the wave equation. It is a second order partial differential equation. At some level, it might be the most sophisticated or most advanced piece of mathematical symbolism that we've encountered yet, at least together. And it might be, depending on what math classes you take, and it has a lot going on. It might even look intimidating. Let me write it again on the, but I'll say this. Any physical phenomenon that can be described by that is what we would ultimately experience as and call a wave motion or a wave pulse. Anything that can be described by that math is a wave, and anything that you would ever experience or describe or observe as a wave pulse, such as, ripples on a pond, or the tides coming in at Far Rockaway, or those ripple. Well, actually, wait, let me be even more clear. To be really clear, specifically what this is about is like the ripples that went back and forth on that long string that you either actually held or you simulationally, computerly held in lab 3. But so strictly speaking, actually what this is the one-dimensional wave equation, I should say. Strictly speaking, this describes any kind of ripple that you can imagine pulsing back and forth or cyclically along a one-dimensional medium. So like ripples along a string, and that string could be a violin string, could be a guitar string, could be a piano string, for example, right? So and then anything that you ever see at the ocean or ripples on a pond or anything like that would be a two-dimensional version of this. And then there's three-dimensional versions of this, etc. But so strictly speaking, this is the one-dimensional wave equation. Anything that is a wave that you ever experience as a wave is describable by this math. And anything that's describable by this math is a wave pulse. And let me also say, I'm going to turn the page a second, and I know the lighting is still weird. I'm going to try to change that in a second. But let me also say before, so I really want to unpack the math. I think the math is beautiful. I think this is where math starts capturing aspects of nature that I literally can't capture in English. I mean, I'm going to try, but this is where I start really believing in the richness of the language of math, is when a few symbols can be put together in such a small package like this and capture so many implications at the same time. Like that's what I'm ultimately going to hopefully get you to see as you get more comfortable with this equation, is that there's a lot of information and a lot of relations being packed into a very small space of symbols right here, which is why it might be intimidating at first, depending on who you are, what you've seen before. You might be looking at this and thinking like, what? Like, I don't even, like, I can barely. So I'm going to try to translate it first, but this thing is the one-dimensional wave equation. And let me say one last time before I go on, when I say the one-dimensional wave equation, what I literally specifically mean is that this assumes pulses or ripples or peaks and troughs, if you like, flowing cyclically throughout a one-dimensional medium, such as a one-dimensional string, or such as the entire example that we constructed to derive this equation, such as like a long row along a horizontal axis of a bunch of little vertical oscillators, okay? This assumes that the collection of physical vibrating particles, known as the medium, through which the wave pulses propagate, this assumes that the collection of oscillating particles, known as the medium, it assumes that that medium occupies one dimension of space, okay? I mean, the whole phenomenon as you'll see, the whole phenomenon requires at least two dimensions of space to even happen. Like, again, let me say, like in our whole example that built this up, we had a row of oscillators of masses on springs building this thing. And then each mass on spring, each oscillator oscillated vertically, right? So there were things happening in the y-axis and in the x-axis and happening in time necessarily for this wave pulse to occur. We actually did require, at least in our setup, one dimension of time and at least two things happening in space. But the collection of particles that were doing this complicated dance that we call a wave pulse, that collection was strewn out throughout one dimension of space. So it's called the one-dimensional wave equation. Okay, I'm going to turn the page. I'm going to try to just going to write it again. Okay. Now, let's start on the left hand. So I'm just going to try to break this down. Like, we derived this equation on last Thursday. Like, we showed where it came from, and I hopefully might be able to, or we showed one way of deriving it anyway. I mean, we derived it from that cosine thing. We derived this from picturing a collection of oscillators. The collection was along the horizontal axis. Each oscillator was free to oscillate along a vertical axis. All the oscillators were identical in their physical parameters, right, in their mass and spring stiffness. Therefore, they were all identical in their angular frequency. They were all going to oscillate at the same rate. We set them up so that they'd also be equal in amplitude, like, you know, go back and forth between 1 centimeter below an equilibrium position and 1 centimeter above or something like that, right? So we made them all identical in every way, but what we intentionally did was we staggered them all in phase, right? We staggered the moments in which the pieces of the cycle at which they each began. We staggered that by a constant amount. That was the key, right? And so we pictured like, and wrote that out as y equals a cosine quantity omega t plus or minus kx. I'm backtracking here, but and capture the entire collection of oscillators with that one function, that one expression that made vertical position y be the output of two independent inputs, right? Y, I mean, again, I don't want to write it here because it's going to clog things, but remember this second order partial differential equation that we're now dealing with here, it came from differentiating twice a cosine expression that had a t in it like we're used to, but also had an x in it. And that was the first time. We had a cosine expression of two independent variables. Together, they spat out one dependent variable. The independent variables were time and horizontal position, like t and x. The dependent variable was y, okay? Well, and we took two derivatives of that. The thing is, we started writing derivatives with these new funky scripty looking D's. Okay, again, like we've only been using these symbols now for one class. So if you weren't in your last class or you spaced out even for 1 minute, one thing you might be intimidated by, or one thing you might be confused by in this expression is like, what the heck are those like things that don't really look like D's, but sort of do? What those are, they are like derivative symbols, but they're new symbols that we're now using, that we use whenever we're taking derivatives of functions of more than one variable, like from here on in life, if you have a function of more than one independent variable, a multivariate function, right? And if you want to take derivatives, what we established last time was it is totally plausible and reasonable and meaningful and doable to take derivatives, rates of change, with respect to one independent variable at a time. You can look at how the output changes with respect to one input while holding the other input constant in your mind, right? That's what we were saying last time. That to do that is called to take a partial derivative. Now, my argument is that, I mean, that's a really cool thing to be able to do mathematically. And again, I am not assuming that any of you has ever done that before. Like maybe some of you have, but and that's terrific, but I'm not assuming that. Not a requirement of this class that it is not a prerequisite for this class that you've ever thought about taking a partial derivative before in your life. I'm teaching you right now. I'm saying it's a thing that can be done mathematically. And the reason I feel like it's a fair thing to bring up in science or whatever is because, in fact, it's scientists who have been doing this for hundreds of years. You guys, well, you haven't been doing it for hundreds of years. I think, but although Daniel probably has been. He was probably like sitting waiting for, and Nikaya, like they've been doing it since they were waiting for class to begin. Okay, anyway, my point is that every time you do an experiment, whenever you do a scientific experiment, particularly, let's say a physics experiment, when you collect data, if you really think about what you're doing is you're holding a bunch of variable quantities constant, and you're deliberately, like this is what the scientific, when people say like, well, all other things being equal, or when they say controlled variables, or when they say, there's one other expression for this, when they say like, controlled variables, whole other things equal, or when they say separation of variables, I guess that's another expression. When you do an experiment, when you think about it, what you do is you hold a bunch of measurements or a bunch of quantities or a bunch of properties that could be changing. You hold them fixed in your mind and you just deliberately tweak one variable and you watch how another variable responds to that. Very specifically, that's what you did in lab 3. If you took a movie if you shook a string and made wave pulses go back and forth on that string, and you took a movie of those wave pulses going back and forth on that string, right? Taking the movie wasn't doing this, but then collecting data from that movie, if you at one point, if you just isolated one freeze frame from that movie, one frame, right? And you actually and you looked at the shape of the string in one frame of the movie, and the string was like this, and you superimposed that picture of that string that was like this, like that one frame that you took of a movie of a string wiggling back and forth. If you impose that string on a background of coordinate axes, like an x-axis and a y-axis, and then you made a scatter plot out of that, and you said for any given x position that I look at, what's the y position of this string? If you think about what you're doing when you did that, what you were literally doing was you were holding time constant. You weren't believing that time isn't flowing. You weren't asserting that time is not flowing. You were just saying, hold on, let me focus my attention on one moment of time. You, in your mind, you set t equal to t naught, like you picked one moment of time, held it constant, and looked at how y varied as a function of x. You looked at the cosine shape that the string was manifesting right at that one point in time, right? And then you got a graph of that, and you use log or pro or some program or whatever to do a curve fit and figure out, oh, it's like a cosine, blah, blah. Then you also, or if you, or presumably, you also went back to your movie and let it flow, but you picked one space, one horizontal position in the background of the movie, maybe a place that was conveniently nearby, some meter stick or something that was sticking up. And you said, I'm just going to watch this one horizontal position and you let the movie flow. And you watch as a piece of string goes up and down along like a reference line or a meter stick or something that was there. You watched as string went from here to there, to there, to there, back to here, to there, to there, to there, back and forth. In other words, you picked some X value and you let Y vary as a function of T to see what would happen. And when you plot those points, now there you literally have to plot them out. Like you get a table of values at this moment in time, the Y, the vertical position of the string is this. At this later bit of time, the vertical position is this. At this later bit of time, the vertical position of that. You get a table of values and you put those ordered pairs onto coordinate axes, you get a scatter plot. And lo and behold, once again, you get a cosine graph. Right now, what have you done when I know I'm repeating myself as from last time, but I'm just trying to emphasize that when you did that, when you separated the variables, when you collected data and you held some factor constant in your mind, again, you're not claiming that time wasn't flowing. You're not claiming that there weren't different X values that you could have picked, but you're just picking one and focusing your attention on the relationship between how Y changes when the other independent variable changes. That's in effect taking a partial derivative. Okay, that's the physical version of what now these symbols mean here. When we take a derivative of a dependent variable with respect to one of its independent variables, while holding all other variables constant. When we just look at how Y is varying with respect to T, we call that the partial derivative of Y with respect to T. Okay, so what's on the left-hand side here is that it happens to be a second derivative, just because we love second derivatives, well, because we took two derivatives. And why do we always take up two derivatives? Because F equals MA. But anyway, so on the left side here is second partial derivative of vertical position with respect to time. This is light, okay? So I'm trying to break this down. This is I don't know if you can read this. Okay. So I'm just trying to unpack the equation right now. Okay. And I know if everybody was always a fine line, I might be boring the people that really were paying attention last time. If you were paying attention, you know where we got this equation from. What I'm now trying to say is what it means. Okay. So the left side is the second partial derivative of Y with respect to T. And again, partial is not supposed to intimidate you now. It's just that concept that I just explained. And it comes up whenever this all assumes why we're having this funny, why we're taking partials now is because we now have a string that is shaking up and down. So at any given moment, the height of the string is a function of both what time you're looking at the string and where on the string you're looking. Right? Like we have a string that's not only bumpy, it's not just a wiggle, it's wiggling in time. Like this is what a wave pulse is. I mean, in short, what I'm really trying to say 1,000 different ways, I'm trying to say what a wave pulse is harmonic oscillation in both time and space. It's cosines happening in time and in space. Harmonic oscillation is just cosines happening in time. A wave pulse is that plus space. You'll see that more and more. Okay, but so the left side of this whole wave equation, the left side is the second partial derivative of vertical position with respect to time. It is simply, in other words, if you look at the blue that's kind of faint right underneath the red, what that left-hand term of the whole equation is just acceleration along the vertical axis. It literally is A sub Y. Right? Because like velocity is the first derivative of position with respect to time. Acceleration is the derivative of velocity. It's the derivative of the derivative. That's what acceleration is, right? Always has been. Now we're just acknowledging we've got more than one dimension of space going on here. We've got a Y dimension of space and an X dimension of space. So I'm just saying second derivative of y with respect to time. What does that literally mean? It means acceleration in the y direction. Literally, it just means if you focus your attention on any little piece of the string, any little piece of this rippling thing that we're looking at, this pulsing thing, this pulsing medium, if you look at any bit of string, the rate at which it is accelerating along the y-axis, i.e. accelerating toward the equilibrium axis, toward the horizontal line, toward the flat base with the string would normally just be sitting at, the rate at which it's accelerating toward that is precisely what we mean by this left-hand side, okay? One last thing to say about that, it's just like d2x dt squared, the left-hand side of Hooke's law. Like, right? I mean, again, I'm worried about turning the page and getting this thing all confused, but remember, what we've been having for a while in this class was, we started with Hooke's law, F equals negative kx, and we said, oh, F equals ma, so negative kx equals ma. So then we got this, our first differential equation of the class, turn back your notes or something, was d2x dt squared equals negative k over m x, right? That was just Hooke's law in mathematical form, was saying the rate of change of the rate of change. If we were picturing a mass on a horizontal spring going back and forth, like, you know, thing on spring, homework 1, mass on a spring going back and forth in a horizontal axis, we came to the understanding in the last question of that homework that that whole situation, the mass going back and forth, could be expressed as d2x over dt squared, i.e. second derivative of x with respect to time, equals negative k over m x. That's what we found. That's Hooke's law. That's the second order differential equation for harmonic oscillation, right? Which we saw until we were blue in the face. The left-hand side of that was the acceleration of the mass, in that case along an x-axis, the rate at which the mass was accelerating toward its equilibrium position. Happened to be on an x-axis. We eventually realized that we just happened to have a mass going back and forth along an x-axis. We ultimately realized we didn't have to have a mass going back and forth along an x-axis. We could have had a pendulum bob going back and forth along some arc of a circle, right? Or we ultimately decided, oh my God, anything that can be described by that differential equation is an oscillator. So any dependent variable we wanted, if its acceleration was proportional to the dependent variable itself, then we said, oh, that's oscillation. Okay. So that's what's happening here so far. I'm saying the left-hand side of this equation is perfectly analogous to the left-hand side of Hooke's law. It's merely referring to the rate at which some particle accelerates toward equilibrium. Okay? That's so far. That's the left side of this. It's just, it's acceleration. I'll write it one way. And I'll even put it this way, acceleration home. It's the rate at which, so the left-hand side means pick any piece of that rippling string you want in your mind. Picture any little particle of string that's going, you know, like the long string that you're shaking one end and a ripple is going to the other end. Picture any little piece of that string. What the left-hand side of this equation is referring to is the rate at which that little piece is accelerating home. What do I mean by home? I mean toward equilibrium. What do I mean by equilibrium? In the case of a long string, I mean the equilibrium axis, the x-axis, the flat line that the string would be lined up at if nothing were happening, right? Okay, oh, sorry, accelerating towards, yes, exactly, Sam, perfectly, yes, exactly, accelerating toward, that's perfect, toward y equals 0, which is just like a mass on a spring accelerating toward x equals 0, perfect, yes, exactly, I'm just moving, sorry, but yes. Should I say yes one more time? Wait, do I get points for acknowledging Sam's existence? No, I don't, because that's my job. But she does exist, in case anyone's okay, this didn't help at all, and my equation thing just got wackadoo. Hold on. Boom, boom, sorry. Okay, I don't know what's going on there. Okay, that's the left-hand side. Now, what's the right hand? Now, the middle term in parentheses, is ultimately the point of this class. If I ever get to it, is ultimately what I want to talk about. But for the moment, let me just point out that it's a constant. I mean, literally, it's one constant divided by a different constant all squared. And I know, by the way, on the first page, I squared each one. And then this page, I squared the whole quantity. That's an arbitrary choice. I sort of on purpose did it two different ways just to enforce to you guys that it makes no difference whether you put the square on the outside of the parentheses or the inside. Okay, it really makes no difference. But the key is that omega is that good old omega is an angular frequency. It's a constant. K, a little bit newer to us. We might be still getting used to it, but K is also a constant. It's technically called angular wave number. We're going to talk more about it again in a second. But just like omega is angular frequency, it's number of radians undergone per second, which is to say number of cycles, sixths performed per second. K is number of radians per meter, the number of cycles that we fit into a length along the x-axis. It's perfectly analogous. Omega, if you understand omega at all, or you're getting used to it, omega is to time as K is to space, like literally. Again, I'll go over it more, but whatever it is, they're both constants. In fact, they're constants that are determined by parameters. Remember, in an oscillator, omega is like square root of K over M or something like that. It's fully determined by the material ingredients of the system. And my point is that omega and K are constant. So if you put a constant over a different constant, what you still have is some constant. If you square that whole sucker, what you still have is a constant. So for the moment, what that term is just a constant. Meaning that it gives me a chance to talk about this term for a bit. I'm probably going to turn the page. So this term is another second derivative. A little bit intimidating. This is the first time we've ever had an equation that has like derivatives being related to other derivatives. It might even look redundant to you, or so it might even look like you could divide both sides or something, but it's not redundant because what we have on the left side is a derivative with respect to time. And on the right-hand side, we have a derivative with respect to space. What we're literally saying here on the right-hand side, and I don't know if I could actually fit this in without making a mess, but what this is second partial derivative of, again, vertical position, like y, again, is in the numerator. Y is being treated as the dependent variable here, of vertical position. But now it's with respect to WRT. I hope that's with respect to now, not time, but the big difference, what's in the denominator here is X, i.e. horizontal position. Now, what's going on there? So that is different. I mean, that is different words, certainly. That is not acceleration. Acceleration is derivative of velocity. Velocity is derivative of position with respect to time, right? Acceleration is second derivative of position of any kind with respect to time. This has nothing to do with time. This is second derivative of y with respect to x. Now, you know about this from math. It just may seem out of context here. When you were first ever learning about derivatives and in calculus, oh, maybe it's in the, I think I just saw something in the chat. Maybe this is in the chat. Oh, no, that was the accelerator. Okay. But I'm opening, if anybody wants to put anything in the chat, you know the word. There's a word I'm looking for, and I'm going to say eventually, if no, the second derivative that stares us in the face on the right-hand side of this equation, it's rate of change of rise with respect to run, when by run, we don't even mean time anymore. Like, in other words, on this right-hand side of the equation, we're now picturing one snapshot of time. We're picturing that we held time constant in our mind, and we just took one frame of the movie, of the stuff rippling back and forth, right? And we just took one frame. So we're literally looking like this stupid blue. Well, we're literally, I don't, and again, I don't want to make this too messy, but like, imagine we took one snapshot of this string, and we just saw it at one freeze frame of its ripply motion. And at that one moment, it's not straight, it's all bent like that. And if we imagine that picture of the string being superimposed onto axes, which is, again, I think what you did in the lab simulation in lab 3, we would see that for any X value you pick, for any place you look along the horizontal axis, the string has a certain given height along the Y axis. What we're talking about here on the right side of the equation is we're talking about picking some random point and looking in effect at the slope of that point, right? And that's a big hint as to what I'm getting at. Like, remember when you first looked at derivatives in a calculus class, when you first looked at derivatives of functions, of arbitrary y equals f of x functions, and you put them on graphs, you didn't have to be thinking about time. You didn't have to be thinking that the x-axis represented necessarily anything in nature or the world or anything. You just had values, input values that you called x and output values that you called y, right? And on a graph, they have this spatial organization. The input values are like arranged according to horizontal space, and the output values are arranged according to vertical space, right? And when you were first learning about calculus and stuff like that, you might have said something like, oh, the derivative, the rate of change, the instantaneous like rise over run of a graph of some point in this yx graph, the derivative could be understood as being slope, or specifically slope of the tangent line to the graph at that point, right? Like there was this understanding when people first learn about derivative, they understand that what it is slope taken to the limit, slope delta y over delta x taken to the limit as delta x gets arbitrarily close to 0, right? Derivative is slope, slope is derivative. As long as you understand that when you say slope, you mean on a graph. Derivative of a function is the slope of the graph representing that function, right? So derivative, rate of change, was like steepness of graph. Rate of change, derivative of derivative, second derivative, could also be understood graphically, could be understood in a pictorial kind of way in your mind and read off the graph. This is where I'm going to stop. I'm going to ask in the chat to see if I'm crazy or not. Like when you first learned about differential calculus, if you think, well, here's the analogy. Here's first derivative is to slope as second derivative is to what? There's a word I'm looking for, like a word that describes the shape of the graph, kind of like how flat or not flat it is at a point. A word that refers to the shape of a graph, and it's not steepness. Steepness is captured by the first derivative. But what aspect of the shape of a graph is it that we think is captured by the second derivative? You'll know, as soon as you hear it, I guarantee almost all of you are gonna be like, oh, that's what he's looking for, that word. Like you'll all know the word. You just might, yes. Awesome. Awesome. Oh, and I should have given people more time. I'm saying, yes, that's awesome that Sam has participated. It is awesome that she has been, no, it's it's not you. No, that was great. What I should have done is said, thank you for your contribution. Maybe you're right, maybe you're wrong. Let's see what other people have to say. That's what I should have said. I'm a bad person. I'm totally going back to teaching school. But no, that was totally right. And I should have just waited to let other people have like a turn to weigh in also. And they honestly, anybody still could now, really. I'm saying, tell me, in fact, I'm desperate for it. Could anybody else confirm or deny? Do you know what Sam's talking about? I'll read the chat out loud. What Sam's saying is that if first derivative of a function measures the slope of the graph for that function, then second derivative of a function measures the concavity of the graph for that function. Like that's what she's saying. That is what I'm saying. Can I get any confirmation or denial in the chat that you've heard this before, that you know what I'm like, whether or not you would have thought of it? Does it ring a bell that second derivative goes with concavity? And yeah, awesome. Thank you, Stephanie V. I'm totally, I hope that was public chat. Sorry. Oh, yes, it was. Okay. Thank you, Stephanie V. That's awesome. And in fact, we're even going to say like what Stephanie just did, like I'm going to take it because she wrote, yes, I'm going to take that not as an acknowledgement of my existence, but an acknowledgement of Sam's existence, because my existence, I've confirmed for my own needs. So like that would count as like cross-pollination, multiplayer co-op. Right. Okay. I think, therefore, I am a hamburger. No, and believe me, I've got things to say about that. Okay. Anyway, yes, very Cartesian. Oh, isn't that interesting? Here we are talking about Cartesian graphs, and Sam is bringing up the Cartesian dictum, cogito ergo sum. Like, it's one guy, that same guy that made these stupid graphs that you have to live with, that aren't stupid at all, but seem stupid for like the first 20 years of your science career. Like, you have to live with these things because of the guy that made them up, who's the same guy that said, I think, therefore I am. I mean, that dude like thought about a lot of things, and no wonder he existed a lot. But but thank you, Stephanie, and thank you, Sam. Could I get just so I don't think like I've like overly ADHD'd everybody here, could someone else besides Stephanie or Sam just confirm, are you familiar with concavity as a concept related to graphs? Could anybody else, and it's for total points, could just somebody confirm or deny in the chat? Concavity, second derivative, like, is this ring a bell? It doesn't have to bring a happy bell. You might hate it, but could someone else acknowledge that you've ever heard this before? Oh God, I'm looting it. Yeah, thank you, Ava Rani. Yes, points for there she goes. That's awesome. And just for that, maybe I'll even pronounce your name correctly one more time in my life. Thank you, Ava Rani. Maybe I'll even, yes. Okay. Thank you. Oh, that's nice. You just acknowledged me. So you just got points. Everybody's getting points. It's all about points. It's all about points in space and time. So, okay. Thank you, you three, and everybody else, Sam, Amarani, and Stephanie. Here, now, where am I going with this? I don't know. Would you go there already, Averbaum? Where I'm going with this is the right side of this equation is not referring to acceleration. It has nothing to do with time. The right side has to do with shape. Has to do with literally at some moment in time, what's happening in the curvature of the string, like literally the string. Like, imagine a photograph of the string at some moment of time being superimposed onto coordinate axes, like a graph that literally just is that string, or picture the string as a graph, because it is, as long as by the x-axis we actually mean x space, and as long as by the y-axis we actually mean y space, right? Well, then what the right side is referring to is the concavity of the graph at a certain point. Now, what does concavity means? It means how not flat something is, how much like something is very, very concave up if it is very, very much like a bowl, right? And it's very concave down if it's very much like an upside down bowl, whatever. And it's very much not concave, like it does not have positive nor negative concavity if it's very flat, right? So now look what this thing is saying. Look what this wave equation is saying. It's actually saying something so like reasonable and straightforward, you'd almost think you knew it before, and maybe you did. What it's saying is to be a wave pulse, for something to be wave pulsing, for our eyes to look at something and go, oh, look at that pulse going down the string. And remember, in the background of all this, one of the reasons I'm going to talk about wave pulses, like for the rest of the course, one of the reasons that whole courses are devoted to wave pulses or wave motions is it's such a cool thing, wave motion. Remember, when you see a wave pulse moving from left to right along a horizontal string, what you're seeing move is not a thing, right? I mean, please remember that. I tried to say that last time, but the whole thing about wave pulses is they totally exist in every real way, except for existence, except for they don't exist, right? I mean, what do I mean? I mean, again, like you see a pulse traveling along the string from left to right, and it's not, you don't just see it with your eyes. It's not an optical illusion. You could literally measure the space that the wave pulse traverses from that one end of the string to the other. You could measure that space with a ruler. You can measure the amount of time it takes to do that with a stopwatch. Everybody in the room will agree when the experiment has begun and when it ended. I mean, they won't perfectly agree, and your stopwatch won't be perfect, but that's true of baseballs as well, right? Everybody in the room can track the motion of a wave pulse just as accurately, just as reliably, just as systematically as you could track the motion of a baseball or a planet or an electron, if you like, right? You're tracking this pulse that goes across and you're like, oh, it just traveled 100 centimeters and it did it in 3.5 seconds. So I guess it'll travel the next 100 centimeters in 3.5 seconds. So I can predict when it's going to be over at the next person. And your prediction will be just as right as it would be for a baseball. Actually, it'll be even more right for reasons we're eventually going to get into, right? So you see this thing actually move in an observable, measurable, analyzable, predictable, i.e. scientific way. The freaking pulse moves across a string, but, and all that's moving is string, right? You're looking, you're like, string is moving, there goes a string pulse. But is any piece of string actually going from here to there? No. Like literally? No. The only thing that's moving is string, and the motion is from here to there, but no string is moving from here to there. That's the essence of a wave pulse. That is psychedelic in itself. Like really, like that is really weird that something is moving whereas no thing is moving. What is moving? The shape of the string is moving. A disturbance in the medium of the string is moving. You could say energy is moving, you like, but that just begs the question, what the heck does that mean? You could say information is flowing, perhaps, and I think that actually gets closer to the truth. Whatever it is the ripple is rippling across, and what this equation is saying is, you know what it means to ripple? How it works to ripple? It means this. It means if you focus your eyes on any one little bit of that string at any time, anywhere you want, like once you get this thing going and waves are happening and you're like, look, waves are happening. And then someone else is like, what do you mean exactly that waves are happening? Like they're so clear, but they're so elusive at the same time. What exactly do you mean? What you could say is, I'll tell you what I mean. Glad you asked. Here's what I mean. I mean that if I pick any point on this string at all, at any time, and I start observing that point, what I will find is left side, the rate at which that point is accelerating home, the rate at which it is accelerating home back to the equilibrium line is directly proportional to the concavity of the string at that point. What? Yes, let me say that again. And really, this is what we're saying is acceleration is directly proportional to concavity. You might have until this point maybe even thought they were the same thing. I don't know. But no, I'm saying second derivative with respect to time is directly proportional to second derivative with respect to space. I'm saying rate of racing back home is directly proportional to distortion from home. What? Let me say it again. Let me say it a different way. Let me remind us of Hooke's law. This whole thing is based on Hooke's law. That's why we spent 85,000 years like unpacking homework 1, because it's really all about things on springs. Hooke's law said, if you'll recall back, hold on, just sorry, getting a little excited here. But this stuff really, seriously, I can't fake this. And I'm not making this up, obviously. Only nature could make up something this cool. Now look at what look, remember what Hooke's law said in the first place. The whole thing of Hooke's law, the whole thing that got us into differential equations and all this funky abstract math, what got us in there was that Hooke's law in the first place was this weird kind of self-referential relationship. It said the rate at which the mass accelerates home to its equilibrium spot, the rate at which it accelerates home to its equilibrium spot is directly proportional to its displacement from that equilibrium spot. That's what restoring, that's what F equals negative kx is really saying, that the farther away you are from home, the harder you're pulled home. That's what it means to be elastic. Like literally, that's Hooke's law, right? Okay. So the mass was equal in the case of a mass on a spring, equilibrium home was a spot, was a zero-dimensional point called x equals 0, right? Like literally it was a point, x equals 0. We were moved, if we were the mass, we were moved away from that 0 along some line, some x-axis. So we were displaced along one dimension of freedom, 1 degree of freedom. We were displaced from that home spot. And it turned out that the farther away we were from that spot, the more we were displaced along one axis from that spot, the harder we were pulled in toward that spot, the greater we accelerated, F equals ma, toward that spot. That's the essence of elasticity, restoring force, whatever you want to call it, like that differential equation. captures elasticity. And then when you solve it, you find out the solution is a cosine function. The kind of motion you get is harmonic oscillation, right? Now, what I'm saying is, look what we have here. Here home now, I'm just looking at the time, home now is no longer a spot. This is sort of like what Sam said like 20 minutes ago. Home is not x equals 0. Now home is y equals 0, meaning home is the flat line, the x-axis for the string. In other words, I don't care. You don't care. When you do lab 3, when you shake a string back and forth, nobody cares where your string is. It's not like the string needs to be 3 feet off the ground or needs to be 7 feet off the ground. It's not the position of the string that matters. It's the orientation. It's that the relaxed equilibrium state of the string is to be a horizontal line, right? Equilibrium is now a line, an orientation, not just a spot, a one-dimensional orientation. The string gets bent, like someone shakes one end, it gets disturbed, perturbed, contorted, distorted. You look at any little spot on the string, it's any little spot. Maybe it's above the horizontal axis, maybe it's below. What is it doing? It's racing back home. Just like the mass on the horizontal spring was racing back home. Only here, home now is like this long string, right? So you pick any little spot. And what we're saying on the left side is, oh yeah, that little spot is racing back home. It's accelerating to equilibrium, and it's going to accelerate just like Hooke's law. It's going to accelerate at a rate that's directly proportional, like it's equal to a constant times what? Not times its displacement from the spot, because it's not, in other words, on the right hand, I'm saying that this wave equation looks just like Hooke's law. It's identical to Hooke's law on the left side. On the right side, though, instead of having x, instead of having a variable, the dependent variable, we have a whole new derivative. That looks intimidating and crazy. It looks like a whole harder thing, but it actually makes sense. What we're saying on the right side, we're saying, oh yeah, the rate at which we're accelerating back home is going to be directly proportional to like some aspect of the way in which we're not at home, right? Only here, we're not just displaced from home. It's not just that we're far away from a particular spot, because there is no spot that anybody needs to be. It's that the whole string needs to be flat. Home is now flatness. So the right-hand side of this equation is not just an X or a Y. It's not just saying how far away you are from the equilibrium position. It's saying how concave the string is, how not flat the string is. It's saying the more bumpy the string, the bigger the bump at a certain point, the more that bump accelerates toward flatness. The bigger the bump, the more quickly it unbumps itself. Just like in Hooke's law, the farther away you are from the home spot, the faster you race towards the home spot. Here we're saying the farther away you are from flatness, the more contorted or distorted or perturbed or bumped or concave the string is at a point, the faster it races back to flatness. This is a restoring force in 2 dimensions rather than just 1. This is what happens if you extrapolate the Hooke's law cosinusoidal restoration oscillation phenomenon. If you blow it up into not only time, but 1 more dimension of space, what you get is a wave pulse. A wave pulse is Hooke's law happening in time and in space at the same time. Okay, this is saying, one last way, I'm saying acceleration is directly proportional to concavity. That's what the wave equation is saying. When you think about it that way, it actually is not, I mean, it actually makes sense, I think. Now, I think that's exciting. I do have to go on though. We have like 11 minutes. What I want to now unpack somewhat quickly is that constant. Like, it's good enough even just to say that the constant's a constant. It means, okay, the left. So this, by the way, this whole equation, oh no, great question. Unit, great question to look at units. I think the thing I'm about to do, I have to unpack the units of the constant to make this all make sense. Everything does have to match in units. But I think in order to see how they all match, I think I have to look at the units of the constant. So I think I'm going to do, so it does make sense. It's a great question. What I'm about to do either will answer that, or if it doesn't, I apologize. But since I only have 8, then ask me again on but you're right. The units do have to match up. And I'm not sure, do they have to be 1 over m? Wait, 1 over m. I'm not sure m has to be involved. Well, we're going to see in a minute. I think, I'm not sure m has to be involved, but you're right. The units have to match. So forgive me. Okay, yeah, thank you. All right, awesome. Okay, just because okay. All right, so the constant on the one hand just means constant of proportionality. It just means left side is equal to right side times a constant. But what does that constant mean? It says, let's unpack the constant. Okay, I'm going to do this a little bit quickly, but remember, omega is 2 pi times standard frequency, right? Omega is radians per second. There's 2 pi radians for every cycle. So omega is 2 pi times the number of cycles per second, right? And remember, cycles per second is the reciprocal of seconds per cycle. Standard, so I'm saying this sort of quickly, but we made a big deal of this like 2 weeks ago. Omega, F, and T are all intimately related, 3 different ways of measuring the same thing. And T, by capital T, I mean period of time, number of seconds per cycle, right? So omega is 2 pi over T. I mean, you may have to think that through again in your own time, but like it's true. Okay. Similarly, and this is a little bit newer, but you might, similarly, K, okay, we said that K is to space as omega is to time. K is the number of cycles per unit space. K is not measured in other words, in other words, the units of omega were units of radians. So we are all about units here. Omega was in radians per second. K was the equivalent idea measured in radians per meter. So if omega was the number of cycles in 1 second, K was the number of cycles in one. If omega was the number of cycles in 1 unit of time, K was the number of cycles in 1 unit of space. Now we have a name for 1 unit of space, for the space of 1 cycle, just like T period is the amount of time for 1 cycle. We have a name for the amount of length for 1 cycle. You may not have seen in this class yet. You might have seen in the lab, but you've definitely seen it in other classes in your life. I'm going to tell you right now, the name for the length of 1 cycle measured in space unit is called wavelength or lambda. Okay, wavelength literally means the number. Wavelength, lambda, is the length of 1 cycle, the number of meters per cycle. It's the space equivalent of T, where T is the amount of time for 1 cycle. Okay, I'm going a little fast here. I'm introducing lambda. So I'm saying lambda is that Greek symbol that we use to mean wavelength. Wavelength, you've heard in other classes, wavelength is exactly what you would think. It's the distance from 1 crest to a successive crest, or 1 trough to a successive trough. It's the length of 1 cycle. Just like T is the time for 1 cycle, wavelength is, as it sounds, the length measured in meters of 1 cycle. Okay, so whether you've heard that before or not, I'm saying it now. Now, why am I saying it? So that I can quickly. All right. So again, this is an analogy. Anything you understand about omega, K is that, but for space. So therefore, then omega over K, okay, which is that constant that got squared in the thing, just came up, but what is it? Omega over K is 2 pi over t all over 2 pi over lambda. Okay. Again, I'm watching the time, trying to do this sort of. And that's just what omega over k is. So the 2 pi's cancel. And therefore, omega over k is like, you have to, so you have 1 over t over 1 over lambda. When you divide by a fraction, you multiply by its reciprocal, right? So omega over k is lambda over t. And that means and we're just about done here, that means that constant term is the square of the speed of this wave. Like omega is omega over k is length of a cycle, wavelength, over time for a cycle, period. So omega over k is literally like saying, I'm watching waves come in at the beach, and I see that between every 2 wave crests, there's 3 meters. And I watch with my clock, and I realize that between every 2 crests, I have to wait 2 seconds, right? So every time 2 seconds elapses, the whole pulse has traveled or has advanced by 3 meters. Thus, the wave is propagating at 1.5 meters per second. Omega over k is the speed of propagation. I guess that's what the last. This is. I'm saying not v like as in derivative of x. I'm not saying the speed at which any one oscillator like oscillates up or oscillates down. And I'm not talking about the acceleration of any one oscillator. All those values are constantly changing. I'm talking about the speed. This is the speed at which a pulse propagates along the propagation axis, in this case, the x-axis. So I'm saying, and this is my last thing, I'm saying that this equation at the top here has all the information about the wave all packed into one statement. What it's saying is, to be a wave means that at any given point in space and at any given point in time, the rate at which some little particle accelerates toward the home axis is directly proportional to the concavity, the distortion of the medium at that point. And the constant of proportionality is the square of the rate at which the entire pulse propagates along the medium. Like every aspect of the wave is all packed into that one equation there, the wave equation. It's saying acceleration on the y-axis is directly proportional to concavity along the y-axis, and the constant of proportionality squared is the rate of the wave moving, pulsing, propagating along the x-axis. Omega over k squared is v squared for the wave. Last point is, if you remember that omega and k were determined, and this you got to write down. I'm sorry, I know we have literally 30 seconds, but remember, if you understand that I'm saying now v squared is omega squared over k squared. I'll write it as the last thing. V is fully determined by parameters. Remember, omega was like square root of k over m or something like that. Remember, omega didn't depend on amplitude. Remember that, and I'm looking at the time. I promise I'm looking at time, but remember the rate at which an oscillator tick-tock, tick-tocks, tick-tocks does not depend on how big the space of the oscillator is. The oscillator will keep time in time at a rate that is independent of how you arrange it in space. The tick-tock rate of an oscillator only depends on the material parameters of that oscillator. Well, put a bunch of oscillators together, each of whose material properties fully determine its oscillation tick-tock rate, and what you get is a wave pulse whose V, whose propagation speed, fully is determined by those material parameters. In other words, what this shows is not only that the rate at which a wave pulse propagates, not only is the rate fully clear and expressed in the wave equation, but it is constant as can be. If you know what medium you use to make the wave, you know what speed the wave will travel, and it will not speed up. It will not slow down. It will go at one rate that is constant and fully determined by its medium. You will never see a ripple catch up to another ripple. You will never see a ripple in the ocean or in a lake or in a bathtub catch up to and or overtake another ripple. All ripples in one medium go the same speed because the speed is fully determined by parameters. That's it. I'll stay for any questions, but thank you so much for total attention. I will see you Thursday, and thank you for bearing with me for the whole thing. But that's a big deal. That's wave speed. Okay, I'm stopping, but I'm here. But goodbye.